Hello, and welcome to this discussion of heat exchanger evaluation and design. We're just going to go over a couple of brief outlines for how to solve heat exchanger problems using the log mean temperature difference or effectiveness NTU tools that we have developed in the previous presentations for this module. So we typically have two general types of problems. The first is a heat exchanger performance problem. We have an existing design, it's already been designed or built, and what we want to do is analyze it to figure out the temperature differences and heat flow for the given inlet conditions, a given flow rate and a given inlet temperatures for both fluids. So the first step is to find the heat transfer coefficients from a Nusselt number correlation for both sides. Use that to find the overall heat transfer coefficient, and then use that along with the flow rates and therefore the heat capacities of each fluid to find the number of transfer units and the heat capacity ratio. Once we have that, we go into one of those equations or a graph and we calculate effectiveness from the number of transfer units and the heat capacity ratio. Once we have effectiveness, then we can use that by calculating the maximum possible heat rate, which is going to be C min times the difference in inlet temperatures of our fluids. And from effectiveness, then we can calculate the actual heat rate as effectiveness times maximum heat rate. And once we have that heat rate, then we can calculate the outlet temperatures for each fluid. And then we have the information we need. The second major type is a heat exchanger design problem. So in this case, we have the flow and inlet temperature and exit temperature requirements. We already know that, but we don't know what kind of heat exchanger we want to use or the size of the heat exchanger that we want to use. So what we do here is we start by using the inlet and exit temperatures and the flow rates to calculate the specific heats, to calculate the heat capacities of each flowing fluid, to calculate the heat capacity ratio, and to calculate the effectiveness. That's the first step. Then we look at the equation or the graph to find the number of transfer units we need from the effectiveness and the ratio of heat capacities. Now, at this point, if we know we're using a particular geometry, we can go straight to that equation. However, if we don't, we may want to look at finding the number of transfer units for several different types of heat exchangers, because that'll help us evaluate which type we want to use, right? Which type of heat exchanger we would like to design. At that point, we have to make some engineering decisions, okay? We have to decide which type of heat exchanger we're going to design. Are we going to have a concentric tube, counterflow heat exchanger? Is it going to be shell and tube? Is it going to be crossflow? What have you? Because that's going to tell us how many NTUs we're going to need. It's also going to tell us how to find the overall heat transfer coefficient. In this case, U or U prime or UA or however we need to formulate this problem. And then we can use the NTU and the overall heat transfer coefficient to find the total heat transfer area we need. And that area is then going to tell us how many tubes we need or how long we need the tubes to be. Now, this process requires engineering decision making. It's sometimes difficult for students to work with this ambiguity because there's usually not a single right answer. If you have to design a heat exchanger to make this effectiveness and flow rates and so on, you could do it with any type of heat exchanger and you would get a different answer depending on which type of heat exchanger you chose and what other design decisions you make. And they would all be right answers. But then we'd have to pick from among those answers to try to find the one that's the most efficient or the least cost or the least maintenance or something along those lines. It's also important to note that the book is not closed on heat exchangers. Research and development on heat exchangers is continuing. The idea here is to reduce waste heat and save money. There's a lot of focus on heat transfer enhancement. We're looking at things like developing new surface types, using nanocomposites to improve heat transfer or special geometries and fins and things like that, using surface roughness to enhance turbulence, to increase heat transfer coefficients, things like that. There's also some work on fluid enhancement, using nanofluids or special heat transfer fluids to help increase heat transfer rates, things like liquid metals. I also want to make a note here on detail. Both the log mean temperature difference and effectiveness NTU methods look at an overall perspective, total heat transfer, total temperature change. What they don't do is tell you temperature as a function of position or temperature as a function of radiolocation or anything like that. So there's no information from these methods about the internal details of the heat exchanger. If we want to use that kind of information, we need to use different tools. We need to look at things like relap for 1D analysis if we're only caring about 1D behavior. If we want detailed 3D behavior, if we're looking at thermal stresses and things like that, then we're going to need to use CFD to analyze these types of systems.